Hi, Dr. P here. In this video, I'm going to talk about torque. Up until now, we've drawn objects as point masses. So let's say you have, a stick, and there are forces that are acting on this stick. Beforehand, we didn't really care about where the location on this object the forces are acting. So if somebody was pushing up on it over here and gravity's pulling down on it, we would just draw our free body diagram as a dot and have the force of gravity going downward and this applied force going upward. But now we actually care where those forces are applied. Why do we care about that? It has to do with equilibrium. So before, when we were talking about equilibrium, we learned that unbalanced forces cause a change in motion. If you push on something and the forces are not balanced, then that object will accelerate. We can have static equilibrium, meaning an object is just sitting there, or we can have dynamic equilibrium, where that object is moving with a constant speed in a straight line. When we care about the location of a force, that's when this idea of torques come into place. And so I'll mention that just a second. But the important thing to think about here is when the torque is unbalanced, unbalanced torques cause a change in rotation. So given this is my stick right here, if this were put on a knife edge or drilled a hole through it so it could rotate, if I push up on this with some force, this thing is going to rotate because I don't have, this is not balanced. And it's not that the forces on this are balanced, it's that the torques are balanced. So what actually is torque? For torque, we use the Greek letter tau. And the torque is just the force applied times the lever arm. And this times isn't a real times, this times is a vector cross product, meaning that it's a vector times a vector. When we see this in algebra-based physics, this is oftentimes rewritten as FR cosine theta. What this means is that the torque is basically just a way of talking about the force that's applied and the distance from the axis of rotation. So this would be the applied force. And R is oftentimes called the lever arm or the distance from the axis of rotation. If I think about this scenario here, this force is actually being applied in the upward direction. So this would be my force. And then my lever arm would be the distance from where it's rotating. So if I have this and I push over here, then the lever arm is going to be the distance to the push. Okay, the distance from where it's rotating to the push. Okay, now this little piece, this cosine of theta. If you think about, I like to think about torques and how to open a door. Okay, so this is like a top-down view on a door. All right, so here's the hinge and here's your door. When I'm going to open a door, all of the door handles are in the same spot. They're all on the edge of the door here. And we push the door open and it'll rotate around. We push the door open at the very end because it takes a certain amount of torque to get that door to rotate. And we want to maximize the radius, the distance, so that we can minimize the amount of force needed to open it. It's going to be twice as hard to open a door if I reduce the lever arm, the distance here, if this is R and this is R over 2, it would take twice the force to open the door. Now think about opening a door. Instead of pushing end on, we sort of like push on it at an angle. So like instead of pushing the door like this, you like push the door open, but you push at an angle. Now you can think in that case, if I'm pushing at an angle on this door, like this, if I'm pushing here, and then this is sort of the action of my force, this is going to be harder to, like, I'm going to have to push harder than if I pushed straight at the door. So this is where this angle comes into play. So the cosine theta would be the angle between the force and this like lever arm here. Now, you can think of this idea of adding in the angle as we really only care about the force perpendicular to the radius. So we would find this F perpendicular here.